Okay, yeah, the recording has started, so we're just going to proceed. Let me share my screen. Um, yeah. All right, so I guess you can see my screen clearly, right? Sarah, can you please confirm you can see my screen?
Yeah, yeah.
Right. Okay. So, I believe from our last class, right, we started with an introduction to the blockchain. We defined what the blockchain is. We looked at some basic properties, or important properties of a distributed system, such as the blockchain. And I believe we also looked at the evolution of the web. We looked at what we mean when we talk about Web 3, right? We talked about Web 1, we talked about Web 2, and we also what was the other thing we also looked at? So we also took a good look at consensus mechanisms, right? We talked about proof of work, we talked about proof of stake, and I think that was we also looked at the Byzantine fault tolerance problem, which I said is a common problem with distributed systems. And I believe that was mostly what we talked about in the last class. So during the course of this class, we're going to be looking at some other important concepts. I believe that we definitely need to get familiar with in order to proceed with the rest of the boot camp. So for those who are probably looking to live coding sessions. Now we're going to be having a lot of them. Like this will probably be the last theoretical class. Every other thing is going to be mostly practical, or we're going to be getting your hands dirty with Solidity from the next class. Okay, so basically we're going to be covering I think 3 or 4 important concepts today. We're going to be looking at the Ethereum virtual machine in detail, right? We're going to be looking at the Ethereum virtual machine. We're going to be looking at what transactions are, and we're going to be lastly looking at blockchain wallets. Okay, we're going to be looking at blockchain wallets, and finally we're going to be looking at smart contracts. So we are just going to get started with the introduction to the EVM. Let me just admit this person. All right. So well we talked about was Bitcoin, right? It was invented by an anonymous figure known as Nakamoto Satoshi, right? And well, Bitcoin was a groundbreaking technology because it unleashed the unlimited potential of distributed ledger systems. It had one major drawback, and that was that you couldn't exactly write programs or build applications that could run on the Bitcoin blockchain. And I think that was mostly due to the fact that in Bitcoin didn't exactly have like a virtual machine such as Ethereum. And also, I think on Bitcoin uses this programming language called script, which is not exactly Turing complete. So you could definitely not write programs or carry out computations on the Bitcoin blockchain. So it was basically for simple transfers of Bitcoin from one person to another, with the blockchain serving as a ledger or as a record book for these transactions. So basically in 2015, right, I think Vitalik came across Bitcoin blockchain, so it has a very novel idea, right? After a lot of iterations made and a whole lot of study, in 2015 he created Ethereum together with Gavin Wood, right? Gavin Wood was his co-founder. So basically, the whole idea of Ethereum was we could make Bitcoin better, right? Bitcoin was amazing. It was this amazing technology that basically showed us how much we could do with distributed ledger systems. So basically, Vitalik said, okay, this was cool, right? But then we could even stretch the potential for that, right? Imagine having to be able to carry out custom computations on a blockchain. That would be cool, right? Imagine being able to write custom logics, the thing we call smart contracts. So basically, the applications you build on the normal web, like we write codes to carry out different automations and all, right? We could also do that on distributed ledger system such as the blockchain. That was what led to the creation of Ethereum in 2015. So Ethereum was like, I think the thing that made Ethereum so popular was it was the first blockchain with like a Turing complete virtual machine. That's the EVM. Because if I don't get this, as if I'm not wrong, right? I believe even after Bitcoin, we had other altcoins, right? We had Litecoin, Yeah, I could remember, and Litecoin, which was more like a fork of Bitcoin, but with I think Litecoin had these bigger block sizes, so that was one reason why it had faster transactions than Bitcoin, right? But Ethereum came in with something more novel, and that was it had a virtual machine basically that was capable of handling smart contract deployment and execution. So basically, what exactly is the EVM? So, like I said earlier, EVM stands for the Ethereum Virtual Machine, and it's basically a quasi-Turing complete state machine. So think of the EVM as how do I put it? It's basically a state machine. Think of it like a virtual machine. Think of the Java virtual machine and the rest. Basically, that enables you to carry out computations on the blockchain, and it's called quasi because with Ethereum found a way to solve what we call this problem in computer science known as the halting problem. Now, the halting problem basically is a problem that's common with every Turing complete system. So basically the housing problem mostly talks about how it's possible for let's say virtual machine or a system which can carry out computations, right? How can you regulate uh computations that would run
Um, Darlington, I think you're breaking.
forever without stopping? For example, if you fill out fill around a programming language, it's probably done something like creating an infinite loop due to improper conditions, right? Okay, can you hear me now? My network is today. Can you guys hear me clearly? Sorry, can you guys give me feedback?
Yes, I can hear you
I
now.
No,
don't know if you guys can still hear me.
You are
yes,
breaking.
yes, yes. We can very hear you
Hey,
guys.
Chidera, can you hear me?
There's consistency in the network.
Okay, I'm just going to.
When you
I'm going
were
to.
explaining the Turing
Yeah, I'll
complete
just
part.
go out and join again. I don't know. My network is messing up today.
Thank you very much. You break me just send me the test. When I do carry, you know like Tina.
Right. Apologies for that brief interruption. Can you guys hear me now?
Yes, yes, we can
Yeah.
hear you now.
Sorry about that. And you can see my screen, right?
Yeah.
Yes.
Okay, so
Yes, I see
yeah,
your
I was
fine.
talking about the Ethereum virtual machine. I guess that's where you guys lost me, and I said Ethereum was invented in 2015 basically by Vitalik Buterin and Gavin Wood, and it solved one of the major problems that it was not a problem exactly, but it was just something that was absent on Bitcoin, and that was the fact that Bitcoin did not have the ability to carry out custom computations. So basically, Ethereum solved that by introducing the Ethereum virtual machine, which was capable of handling smart contracts and deployment and execution. So basically, in this section, we're going to be looking at the Ethereum virtual machine in detail, and we're going to be trying to explain it in very simple languages we can understand. And I think I'm going to be using the Ethereum book to help us with that. Just going to be referencing this for um, going to be referencing this. Ethereum block. All right, so basically at the heart of the Ethereum protocol is the Ethereum virtual machine, or we call it EVM for short, right? So it's basically a computation engine and is not very dissimilar to the virtual machines you are used to, let's say the Microsoft.NET framework, the Java virtual machine, and so on that you are used to, right? And basically, the EVM in simple terms is just responsible for handling smart contract deployment and execution. So the EVM is, like I said earlier, what gives Ethereum the capability to run custom computations. So basically, simple value transfers from one externally owned account to another would likely not involve it, right? So we've not looked at externally owned accounts. We're going to be looking at it next in, I think when we look at wallets, wallets is going to be like one of the last things we're going to be looking at today. So, but every other thing, right, that every other computation, any other thing that goes on the Ethereum blockchain, right, that involves like a state update is mostly computed by the Ethereum virtual machine. So I was explaining something right now before I got cut off. I said the VM is a quasi-Turing complete state machine. So I'm going to start explaining what a Turing complete state machine is before we now explain what a quasi-Turing complete state machine is. So basically, a Turing complete, I think the virtual machine or anything is considered Turing complete if it has the ability that, if I go to try, if it has the ability to carry out any custom computation, that it has the ability to carry out different types of computation, that there's no limit to the kind of computation that can, if there's no limit to the kind of computation that can be carried out on a machine, that machine is considered as Turing complete, right? And the Ethereum virtual machine is called a state machine because basically it changes state, right? So when the transaction is carried out on the EVM, so state is the state of the Ethereum virtual machine basically is updated. That's why it's called the state machine. Now, fully put, a quasi Turing complete state machine basically. Um, um, so the word quasi there is basically refers to the fact that execution processes within the Ethereum virtual machine are limited to like a finite number of computational steps. Now, this is what I was trying to explain the background noise outside. So this is what I was trying to explain earlier, right? So with any virtual machine or any computer that has the ability to carry out custom computations, there's the chance of having stuff like infinite loops or executions that go on forever. For example, if you during your first time writing programming languages, right? Because I remember it happened to me basically, and I was using just a 4 GAM system. So I wrote a loop right in PHP as a then, and the loop basically had the conditions was not correct. So basically, just imagine saying you want to continue printing hello world in as much as I is probably greater than 1. So there's no condition to, no instruction given to the system as to when it should stop printing hello world. So what happens now is you create an infinite loop. You just keep printing that hello world, or just keeps running until it exhausts the resources of the system totally. So what exactly happened that day was it just kept running until my system kept freezing, and I had to find a way to like shut everything down, right? So that's the problem with most, should I say most Turing complete state machines, right? With Turing complete systems. So the question is now the quasi in this quasi in the quasi Turing complete, right, aims to solve a problem that has existed in computer science for a very long time, and that's something that is known as the Houghton problem. So the Houghton problem basically is just what I explained earlier, right? We want to ensure that executions that are running on our system runs for a while and then get stopped, right? We don't want it to run in until like it exhausts every single resource on our system. And it's even more crucial for a distributed system such as the blockchain, because people are going to be joining different nodes are going to be joining different capacities, right? You want to ensure that we don't have something called like a DDoS attack, right? Where a malicious user tends to want to use out all the resources of a single node. And to solve that issue, Ethereum introduced the concept of gas. So we're going to be looking at gas in if further as we go further, right? But the whole idea of gas basically within the Ethereum ecosystem and something that exists within most blockchains, right, is the fact that when you want to carry out a transaction, for example, on Ethereum, you need to pay what we call gas. So gas is more like the fees you are paying to, let's say, the miner or the validator to carry out those to carry out that whole transaction or an update the state of the EVM, right? Because for, like just I explained earlier, we want to ensure that these guys are bringing in their resources, their the nodes are running with a whole lot of power and a whole lot of resources, right? We want to make sure that a malicious user does not just come and use out all those resources without paying for it. So that was how the concept of gas was introduced, right? So probably you've probably encountered errors like, let's say you were trying to carry out a transaction and then the transaction runs out of gas and it gets the out of gas error. So what happens is the amount of gas that was exhausted during that transaction is deducted from your wallet, but the transaction does not get completed. So it means that the state of the EVM is not updated. But then you notice that the amount of gas was deducted from your wallet to compensate, let's say, the miner or the validator for all the work that was done during the process, all the resources that was used during the process to get to the point where it stopped. So basically, what I'm trying to explain now is how the halting problem is solved in Ethereum is using the concept of gas. So using gas now, we can ensure that there is no means by which, let's say, a malicious user can perform something like a DDoS. DDoS stands for distributed denial of service, right? Where the malicious user probably tries to run, let's say, an infinite loop that will just keep on running until the resources of the nodes are completely exhausted. So that's what it means by. So when we say EVM is a quasi-Turing complete machine, we say that what we essentially mean is that EVM is a state machine that can carry out any computation, but with a limited or a finite number of computational steps. I don't know if you understand that. If you have any questions, you could probably just ask on the group chat. But I also like us to give me feedback because something is sure my network is messy, so I just want to be sure that you guys don't lose me at any point. All right. So going forward, right? So can you guys please mute your mic, unless you want to ask a question? Do you want to ask? Does someone want to ask? Uh, Alex, do you want to ask a question? Okay, Wisdom, I can see your answer. Can you just unmute your mic?
Sorry, you said about gas fee. Can you hear me?
Yeah, I can hear you.
Hello?
Yes, go ahead. We can hear you.
Can you
Yeah,
hear
I
me?
can.
You are like saying about gas fee, that one of the reasons
Hear you.
why the EVM,
Yeah.
the ideology of gas was built. Can you hear me? The ideology of gas was built on the EVM, which is the Ethereum virtual machine, is doing some kind of attack. You say the DOS attack, that some attackers cannot exhaust that computing power, which is, you say that EVM is complete a Turing machine, right? Hello?
Yes. Yeah. I can hear you. Continue.
So the ideology of gas is for attackers, malicious attackers, not to exhaust the computing power of the EVM machine. That's what I want to ask.
Yeah, so basically, the blockchain is a distributed system, so it is built in such a way that we don't have to trust people to do the right thing. We want to ensure that we can curtail or restrict the behaviors that go on within such a distributed system. So we need to come up with rules that should guide the blockchain. Because imagine if people don't have to pay gas to use like a distributed system such as Ethereum, right? There's every possibility, like I can decide to stand up today and I want to just halt Ethereum's operation. It's very simple. I'll just perform like a transaction that could run forever and exhaust the resources of the nodes which partake in the Ethereum ecosystem, right? And when the resources of these nodes exhaust, right, these nodes could probably have a downtime or something, and that way I could successfully take down Ethereum, right? So we want to make sure that should I say, curtailed. Like, we find a way to ensure that people do the right thing. We don't want to trust people to do the right thing. We want to ensure, we want to enforce it through rules that these guys can do the right thing. Now, the concept of gas, like I said earlier, with every Turing complete system, right? There's a common problem known as the Houghton problem, which is that there's a possibility that people could run executions with infinite number of computational steps. Now, this kind of executions will just keep running till they exhaust the resource of your system. And it's very simple to try out. Like I said earlier, most of us have written codes, right? Or probably written two codes. Open your system, through your VS Code, probably PHP, JavaScript, I don't know, whatever it is you want to do. Just write a simple loop, right? That has no stopping condition. So let's say you're writing a for loop that has no stopping condition, right? We find out that it will just keep running. Let's say you run that in the browser, right? It will just keep running and running and running and running until the resources of your system basically is exhausted. Now, if you have a system with, let's say, with less RAM or less computing power, less processing power, you find out that with time, the whole system will just hang, it will just freeze, and you probably have to shut it down and get started again to make it work, right? Now, we do not want this kind of situations within the Ethereum ecosystem. I want to ensure that Ethereum has, let's say, 99 or 100% of them. I want to ensure that Ethereum keeps running. And the only way we can enforce something like that now is by introducing the concept of gas. So the concept of gas, introducing the concept of gas now not helps us tackle the Houghton problem based on the fact that every computation which you carry out on Ethereum, you pay for the steps involved in that computation. So Ethereum calculates the number of steps that is involved in your computation, right? And you are deducted gas for that amount, for that number of steps, right? And in case where you don't have enough gas to pay for that transaction, what happens is that you keep running that transaction until a certain point where you run out of gas. And when you run, just think about gas. I think a simple way to basically explain the concept of gas is using the fuel think of gas as the fuel in your car or in your vehicle, right? So your vehicle will keep running. Let's say you want to go from here to Abuja, right? Your car doesn't care whether you really want to get to Abuja, or if you don't get to Abuja, somebody will die. The only thing your car needs is give it enough fuel and it take you to Abuja. But let's say you want to play smart, or because probably you don't have enough money, you decide to put in a very little fuel. Maybe you can just move from here to halfway, and probably it's just stop you halfway. And then there's nothing you can do. You've probably exhausted the fuel for that number of time, right? But you need more fuel if you're going to get to Abuja, if you're going to get to your destination. That's how gas works. Gas is just like the the fuel basically you need to get your transaction updated or get the state of the EVM updated. So, like as I was explaining earlier, if you run out of gas, that gas is still deducted from your wallet and used to compensate the miners or the validators. That's as at the old Ethereum, right? The fuel was going to be used to compensate the miners and the validators for for all the resources they wasted during that process of trying to carry out a transaction, even though the transaction was reverted. Now, because of this, right, you would not want to run an infinite loop, because if you run an infinite loop, definitely you just end up wasting gas fees and your execution will be stopped halfway. I don't know if that answers your question, Wisdom. I don't know if that answers your question. Yeah, Wisdom, does that answer your
Yes.
question?
Yes.
Right.
Yes. Thank you very much. I understood it now.
Yeah. All right, let's just continue because of time, right? So now I just want to ensure we look at the more important things that we can study, that we can understand, right? So basically the Ethereum virtual machine, basically what the Ethereum virtual machine understands, or what it carries out, is a set of bytecode instructions. But now these bytecode instructions are not something that are exactly on that can be, they are not exactly, a better way to put it, right, is they are not human readable. And that's one of the reasons why we have higher level smart contract programming languages. So for example, for Solidity, for Ethereum, we have Solidity, we have Serpent, we have LLL, and we have a few others too, right? Now what is smart high level programming languages they do, right, is they help you to write smart contracts in higher level languages you can understand, right? Write them in English, and what the compiler does basically, so it's the compiler will just step or convert this uh the the codes you've written right in the high level language to step it down to write code instructions which are understandable by the Ethereum virtual machine. And amongst um the numerous higher level smart contract programming languages which you can find within the Ethereum ecosystem, right? We are going to mostly be dwelling on Solidity for in the course of this bootcamp, right? Because Solidity is like the most popular. Solidity is considered the one of the most safest, right? And is what you mostly find job offers for. So there's also Viper, which is also very popular too, and it's something like I would encourage you to check out probably during your free time. Viper is also a great language. And okay, so now I talked about the bytecode instruction sets, right? Now we have what we call opcode, which are the EVM instruction sets. That basically EVM understands the way you give DVM instructions, right? So we have among these opcodes, right? DVM has the ability to carry out arithmetic and bitwise operations. So DVM can carry out your addition, your subtraction, your multiplication, your division, your modulo, and even different bitwise logical operations. DVM can carry out so also the EVM has the stack, memory, and storage access, which we are not going to be looking at. All those things are going to be a little bit above your knowledge level. We might look deeper into the EVM towards the end of the bootcamp, but for now we're going to just try to keep things simple. So but if you're interested in checking out the opcodes available within the EVM, right, you could check out this document. So as you can see, there's addition to add the two top stack items. There's multiplication, there's subtraction, there's division, and so on and so forth. So by stack, basically Ethereum so I see Ethereum stores or adds these instructions to stacks, right? So let's say you want to perform an addition, just going to pop up the two top stack items and basically carry out the addition opcode between both of them and return the results. So, but we're going to just keep all this is like beyond the scope of this particular class. Now, let's just talk briefly about the Ethereum state, right? So, basically, we tend to see the EVM or Ethereum as think of it as a global world state computer. And like I said earlier, the EVM is like the heart of this the operations of this Wall Street computer, right? So the job of the Ethereum virtual machine basically is to update the Ethereum state by computing valid state transitions as a result of smart contract code execution as defined by the Ethereum protocol. So, okay, so at the top level, we have the Ethereum world state. I want to ensure we don't we just look at things that are important. Okay, so let's just try to make this simple without all these big grammars, right? So, like I said earlier, the EVM is more like the let's say a global world state computer. Basically what you do on computers is you carry out operations that like changes the memory of the computer. In the Ethereum virtual machine, right, it updates the state of the EVM. So when you carry out a transaction on Ethereum, basically the EVM updates the state of this computer or the Ethereum basically from one state to another. We'll see that in transactions. So let's say the state of the EVM was T before you carry out a transaction. If your transaction was completed successfully, right, it takes your transaction from state T to state T plus one. So that's just basically the job of the EVM. It carries out, like I said earlier, looks at this computation, carries it out, and updates the state of Ethereum. Now, we already talked about gas, right? And we talked about how gas solves the housing problem, and this particular point here, right, is just trying to see, think of the EVM as let's say at the point where you want to carry out a transaction, right? Think of the nodes or the miners or the validators and so on and so forth as running a sandboxed copy of the EVM. You know what a sandbox is, right? Let's say like a development environment. So basically, they get a copy of the current state of the EVM and they try to carry out to compute your latest transaction. And if it is a valid transaction with enough gas to process it, right, they update the state of the sandboxed copy, and they're using this sandbox version, right? They add all those new updates and whatever changes that was made to the sandbox version to the main Ethereum version, which is further broadcasted through um the system, right, to all the other nodes. So I think that should be as much as all probably need to know about the Ethereum virtual machine. Um, for now, we're just going to skip all these. All these are not necessary at this point. So you touched about talked on train completeness and gas. We're already running out of time. Said earlier. Okay, Paul, we are going to let's look at how gas is calculated within the train ecosystem. We cannot use this material because this material is already out of date. This does not contain the changes made after the London upgrade. That's the introduction of the IP15 pipeline. So I think we can use this resource to be up to date. This is the official Ethereum docs. Let's check out the gas section. So yeah, we already talked about gas, and we already explained what gas is, right? So here you see gas refers to the unit that measures the amount of computational effort required to execute specific operations on the Ethereum network. Okay, so there was the London upgrade made in August 2021, which made a little update to the way that gas fees were calculated within the Ethereum ecosystem, right? So before the London upgrade, I think gas fees always were usually calculated as the gas limit, right? Times the gas price you're willing to pay to get that's the gas price for your transaction to get like the total gas you're supposed to pay. But right after the London upgrade, there was the introduction of concepts such as the base fee and the priority fee, which is also known as a tip, right? So after the London upgrade, so for the example here says, let's say that Jordan had wanted to pay 301.8, right? So in this transaction, for a simple Ethereum transfer, normally the gas limit is just 21,000 units. And the base fee, let's say the base fee for this transaction is 10 GUI, right? So Jordan is going to include a tip of 2, but I don't know if we talked about GUIs and Ether. I can't remember if we talked about that, but let's just touch on that slowly. What chapter would I find that? That should be in introduction. Yep. So yeah, so Ethereum has the official currency of Ethereum is the Ether, not Ethereum. So I know we're all used to calling it Ethereum, but it's not Ethereum, it's called Ether. Now basically Ether divided into can be broken down into very smaller quantities, right? And for example, we have the way. So the smallest unit of an ether is called a way. So one way, basically, one ether is like 10 raised power 18 way. I think, yeah, 10 raised power 18 way. So almost gets into the call. Yeah, so one ether is equals to like 10 raised to power 18 way, right? And as you can see here, we have Barbie, we have Lovelace, we have Shannon, we have Zabo, we have Fini, we have Ether, we have Grant. So when we talk about gigaway, right? Gigaway should like be 10 raised to power 9. Yeah, 10 raised to power 9 is gigaway. Giga is 10 raised to power 9. So basically, when we say gigaway, we're talking about 10 raised to power 9 way, and that should be like half of one ether because one ether is like 10 raised to power 18. So you could just check out this resource to later to look at the Ethereum denominations, smaller denominations, and all. But that's not what we are looking to look at during the course of this call. So now going back to where we were, I think this was where we were, right? So let's say the gas limit for this particular transaction for simple transfer, right, is 21,000 units, which is then we have what we call the base fee, which is the fee. Now the base fee is the fee which is bond. It is paid to like I said earlier in the previous before the London upgrade. Every fee, the fee paid by the user is basically given to the miner as a compensation for the resources he probably used in executing a transaction, right, and adding it to a block. But after the London upgrade, two things were introduced, right? We now had the base fee and the priority fee. So the total fee a user would now have to pay was now calculated by the unit of gas used, right? The unit of gas he used times the base fee plus the priority fee. Now the base fee is a fee basically that's paid to the Ethereum blockchain. So the base fee is burned out of existence. So the base fee basically paid to to Ethereum, right, is burned out of existence. Then we have the priority fee. Now the priority fee is now think of it as like a tip you pay to the miner to like prioritize your transactions. Because just to understand why the priority fee is important, right? Now miners or validators basically, because currently with the migration to proof of stake, right, we know them as validators, no longer miners. So validators can decide what transaction they want to include in a block, right? They basically go to the mempool and they look at different transactions and they can decide what transaction to fit into a block and what transaction they don't want to fit into a block, right? Now I think this question was asked in the last class, right? And Ethereum has something called a block gas limit, and the block gas limit is basically what determines the number of transactions that can fit into a single Ethereum block. Now this is going to be a little bit complicated, so I just want you to follow me, right? So now a single Ethereum block has I think a maximum gas limit of 30,000 gas, sorry, 30 million gas rather, 30 million gas. Now, although it is not expected that the block has to get filled up to 30 million gas, I think the normal should be like half of that. That should be like 15 million gas. Now, 15 million gas is the base measurement, and it's one of the important criteria that help determine gas fee. So, in a case where Ethereum is super congested and the miner or the validator has to fit in more transactions that exceeds that 15 million gas limit, right? The 15 million gas, right? If it goes above the 15 million gas, with the next block, gas fees would be a little more expensive. But if but at the time where the miner or the validator publishes the block, right, you have less than that amount of transactions that spent less than 50 million gas within the block, right? With the next block, we're going to have transactions pay lesser gas fees because it is assumed that the uh, the system at that point is not Ethereum at that point is not very congested, right? So that's the importance of the priority fee. Now, when you increase the priority fee for a particular transaction, the transaction becomes more should I say it looks more valuable to the validator, because within the distributed system like Ethereum, within blockchains, right, like blockchains, we assume that everybody's in it for like their own selfish gains, right? Nobody becomes in a miner or a validator, right, to play selfless or to promote technology. Everybody's here to like make money. So let's say let's assume as a validator, a miner, I see a transaction with a priority fee of 0.28 or 0.0028, right? And I see another transaction with a priority fee of 0.018. It's just normal human instinct that I would go first for the one with the higher transaction, a higher priority fee, right? Because the priority fee, like I said earlier, is the tip that is always paid to the miner. So it makes sense that I would go with the one with the higher priority fee. I'll include that one in the block first. So this is how you can actually I think this is how you can actually from some transactions, right? Add a higher priority fee, and it would be more, that transaction would look better to the miner. It would look more enticing to the miner or to the validator, right, than one with a lesser priority fee or no priority fee at all. So that's the essence of the priority fee, right? So like I said earlier, the total fee you will pay now will be like in with the new London upgrade, right? It will be the number of units of gas which was used, right, times the base fee set by the system is not something that you set, right? It's base fee set by the system plus the priority fee. The priority fee is the tip that you pay to the miner. So in a case where, like we can see here, you are performing a single transaction, a simple transaction, ETH transaction. So Jordan, for example, want to send Taylor one ETH, right? So I think the gas limit for an ETH transaction, like ETH transfer, is 21,000 units. So let's say the base fee set by the system is 10 GUI, right? So you can see here Jordan includes a tip of 2 GUI to the miner, to the validator, to like incentivize him to add this transaction to a block. So the total gas fee that Jordan will now have to pay will now be 21,000 times the base fee plus the priority fee, which would turn out to be 252,000 or 0.0002528. So that's basically how gas fees are calculated within the Ethereum ecosystem. Now, I already talked about block size, right? I said before the London upgrade. So yeah, before the London upgrade, Ethereum had fixed size blocks. So that was problematic because in times of high network congestion, right, these blocks operated at very full capacity, and users will probably have to wait for the demand for a block to reduce before they could get included in a block, and that led to like a very poor user experience. There's a lot of congestion. But after the London upgrade, which introduced like a variable size block, so each block, the target size now for a simple Ethereum block is 15 million gas. So what determines the number of transactions that can fit into that block is the amount of gas that is paid by each transaction. Now, just to explain this, right? So let's say like I said earlier, the maximum amount of gas that should be paid for a single block is 30 million gas. That's the gas limit. So let's say I carry out different transactions. Let's say I carry out like 10 transactions, right? And the target size is 15 million gas. And let's say that 10 transactions, okay, just to make things simpler, let's say that 10 transactions cost like 10 transactions, sorry, 30 million divided by 3. Each of that transaction costs like 3 million gas, right? And basically the 10 transactions automatically get hit the 30 million gas. So it means that for that particular block, we can only contain that 10 transactions because the 10 transactions already has hit the 30 million gas limit, right? But if there are more transactions with less gas, let's say like 20 to simple air transfers that we're going on 20,000, so I don't know how many 20,000s will fit into like a 30 million. I use my calculator. So but that would be like a lot of transactions because then I just leave that. So basically that's how the number of transactions that can fit into a block can be calculated,
Hello.
basically using the gas that. Hello, can you hear me?
Yeah, can you please slow down? Seems like you're talking fast.
All right, sorry about that. It's just because we are out of time. We have just an hour to go, and there's still a lot to do. All right, I'm just going to try to slow down for a bit. Okay, so I was talking about the block size, right, and the effect that the London upgrade had on the block size. So I was saying that before the London upgrade, the introduction of EIP 1559, Ethereum had fixed size blocks. Now, this was a very big disadvantage because in times of high network demand, when the network was super congested, these blocks were operating at full capacity. And most times, as a user, you'd have to wait for quite a while, right, for the demand on these blocks to reduce before you can get your transaction included. Now, this led to a very poor user experience. So with the London upgrade, right, I think one of the things that one of the changes that was made, right, was the gas limit for each block was increased. Now the target size we are looking at, because let's see, the target size is just 15 million gas. So that's what we want to ensure that transactions can fit in up to 15 million gas, right? But in a case where there's very huge, let's say there's huge increase in network demand and there's a lot of transactions that need to be fit into a block, we can now stretch the block size up to 30 million gas. So it means that we can now fit in more transactions than normal 15 million gas. Now, what I was explaining earlier was this goes a long way in determining the gas fee that we paid to get fit in the next block. So let's say, for example, for the previous block, that was mined, right? For the previous block that was mined, um, the target size of 15 million gas was exceeded because there was, if the target size of 15 million gas was exceeded, the network tends to conclude that okay, there's high congestion or there's high network demand. So what will happen is with the next block, gas fee will increase, I think by a certain amount. I can't remember, but gas fees will increase by the next block. The base fee that will be paid will be increased. But let's say the number of transactions that will fit into a block, right, which was less than that 15 million gas. What's going to happen is with the next block, right, we are going to pay less gas. Gas fees are going to decrease because we assume that there's not a lot of congestion on the chain. So that's one of the things like the variable size block helps do in Ethereum. Although we still face a lot of scalability problems, but it's way better than how it was before the London upgrade. So basically, the base fee now is, like I said earlier, the base fee now that's
Can't hear you, sir.
adjusted in proportional to
Hello, sir, you are breaking.
Sorry, we can't hear you, sir.
how far
I
the
think you are
current block
breaking. We
size
cannot
hits
hear
of
you.
the target. I already explained this, right? So the
Yes, sir,
base
but we can't
fee
hear you. There's consistency in breaking.
for the next
So
block
can
will
you hear us?
can you
No, we cannot hear you. You are breaking.
how about now? Is it better now?
Yeah, it's better.
Yes,
Yeah,
sorry
it's
about
better
that.
now.
My network is like very much messed up this evening. I don't know why. I have no idea why. I had to even go outside. It's still really misbehaving. But so let's just continue and let's see how far we can go today. So like I was explaining the base fee, right? So okay, there's the base fee for the next block will be increased by a maximum of 12, I think 12.5%. Because of time, you can always go through this document really out of time. So I'm just going to space this document. It goes a long way in explaining like how Ethereum gas fees are calculated basically, and should give you a better understanding of how things work within the ecosystem. But in the meantime, we're just going to head over to covering what transactions are and how transactions work basically. Right, but does anybody have any question from the block size thing or the gas fees thing? Anybody has any question before we move on to transactions? Any questions? Yeah, wisdom, I can see hands. Oh, can you unmute your mic?
All this London upgradable, what's the meaning?
Okay, so the London upgrade was just a name for the Ethereum upgrade I think introduced EIP 1559. So basically they're always giving names. I don't exactly know how they are named, but they're always giving funny names. There's Shanghai upgrade, which introduced the ability for people who staked it recently. That's the proof of stake system, right? To be able to withdraw their ETH. And there are also a lot of names. You could just probably go through. It should be somewhere within if you check the Ethereum website, there should be somewhere you'd find all the upgrades that have been made and basically the things that they introduced. So but they're just names basically for the upgrades that the Ethereum protocol will undergo. All right. So in the absence of questions, I think we'll just proceed to look at transactions. So transactions basically are cryptographically signed messages which are usually originated by an externally owned account, transmitted by the Ethereum network, and recorded on the Ethereum blockchain. Now, this is plenty grammar, but let's simply put, right, a transaction is basically what happens. It's how you change the state of the Ethereum network from one state to the another to another. So basically, let's say I send Ethereum to Stanley, right? That is a state change basically, and that happens in a transaction. I think there's no better way to explain this than by actually demoing this, right? So, but simply put, right, transactions. I want one thing I would want us to note, right, is transactions are usually originated from an externally owned account. But this has changed, or this has changed with the introductions of contract accounts. So basically, we are going to be looking at that in blockchain wallets, right? But there are two types of accounts on Ethereum. We have its externally owned accounts, which is the normal type of account. Let's say MetaMask, Trust Wallet, the normal type of accounts we are used to. Then we have contract accounts, which basically introduces the idea of you being able to use custom signer keys or write logic basically into accounts. So it's account abstraction or the introduction of contract accounts. You could do so many amazing things that you would previously not have been able to do with externally owned accounts. So transactions are signed messages which are originated by either an externally owned account or a contract account, and then transmitted to the Ethereum network and finally recorded on the Ethereum blockchain. Remember that the blockchain is a distributed ledger, so it stores record of every single transaction that goes on in the Ethereum blockchain. Now let's look at how we can carry out a very simple transaction. So I don't have MetaMask on this particular profile. Let's let's see let's see here. Okay, so I have MetaMask here, which we're going to use. Uh, I don't have that here. Let me see. I'm actually looking for not minutes. Sequoia slash my Sequoia. Yeah, so as you can see here, this is a wallet. Now this is a testnet account, but as you can see here, it's just Uh, but no, yeah, let's just ignore that for now. So, as you can see, these are different transactions I've carried out on the Sepolia network. So, the Sepolia network basically is a testnet network for Ethereum. So, as you can see, there are different transactions I've carried out: contract deployment, contract interaction, submit solution, and so on and so forth. These are the names of the functions that will be probably called during the course of carrying out a transaction. But let's look at the simplest type of transaction you can carry out, that right? And that's sending Ethereum from one account to another. So first I'm just going to create a new account. Let's just add let's just call this second. Let's create. Now we have a new account here. That's a new Sepoli account, which is called Second. Now to carry out transactions within the Ethereum blockchain, let's say, for example, a transfer transaction, right? Because there are different types of transactions. There are transactions that originate from externally owned accounts, that's from accounts with private keys, public keys, and so on. And there are also transactions that are initiated from contracts. So contracts have the ability to initiate transactions. For example, let's say I built a smart contract on Ethereum that like for example the contracts are going to look out a simple Ethereum name service system that I can use to store my name on the Ethereum blockchain or associate my name with an address on the Ethereum blockchain, right? So when I call the register or the store name function, right, when that function, if I have enough gas fee, would initiate a transaction on the Ethereum network. So these are transactions basically. So just know that most times transactions will either be originated from an externally owned account or a contract account or from smart contracts. Now I want to send Sepulia ETH. I will send a certain number of ETH to this particular account, right? But I need to first of all copy the wallet address. So when we look at wallets, we're going to look at what addresses are. So addresses are basically just think of it as unique bank account numbers you see on the Ethereum blockchain. So I want to send Ethereum to this particular account. So I'm just going to go here, go back to my main account, and I'm going to initiate a transaction. So I'm going to click on send, and I'm going to paste the address I want to send to. That's second. I'm going to click on second, right? Let's say I want to just send 0.001 Sepolia ETH, right? So I'm going to go to, as you can see here, the wallet automatically calculates the max fee it thinks I could pay. Now, the max fee is just the maximum fee that can be paid for this transaction. It also includes the base fee, the priority fee, for this part that the wallet thinks I can pay for this particular transaction. So with the introduction of EIP 1559, right, transaction you use transaction or the gas user in experience is now much better, because even if I don't get to pay, as let's say at the end the system deducts lesser fee than this 0.0000315 Sepolia ETH, which was the max fee that was specified by my wallet, right? The rest of the fee, which was not exhausted, is going to be refunded back to me automatically. And then if you check that document I sent on gas fees, you'll see the calculation for refunds. So we're going to click on next, right? And as you can see here, it says it just gives me confirmation. Okay, I'm sending 0.001 to Sepolia, and this is the estimated amount of fee I'm going to pay for this transaction. Now, this is the total number of ETH I've deducted from my wallet. Now, I'll just simply click on confirm, right? And as you can see here, a new transaction is initiated. Now, we can view this transaction on a block explorer. Now, a block explorer is, think of it as a place where you can view every single transaction that is going on, or that has gone on, or that has been executed on the Ethereum blockchain. For Ethereum, we have what we call Etherscan. We have Etherscan, right? So Etherscan is where it's a block explorer for Ethereum that you can find every single transaction that goes on the chain. So as you can see here, each time you carry out a transaction, there's a transaction hash generated for that particular transaction. Transaction hash is a unique jumble of phrase or words or alphabets and numbers that you can use to find this transaction on the block explorer, right? So this is the new transaction hash that was generated. As you can see, sources indicates that this transaction has been carried out successfully, right, and has been added to the Ethereum blockchain. Then just one block confirmation, right? So this is the gas fee. This is the gas price, the current gas price, probably base gas, right? And this is the total transaction fee I ended up paying. This total transaction fee I ended up paying. Now let's go back to our wallet and see if um, the Ethereum state was changed. So as you can see here, my balance have been deducted for this particular account. It means that the Ethereum world state computer has been updated, right? Now, if you come to second account, you can see your current account is it's not your business. Yeah. So you can see now in this second account that this second account now has 0.001 Sepolia ETH. So we just carried out a simple Ethereum transfer transaction that updated the state of Ethereum. Now, if you check this transaction, right, you can see that the transaction has received basically, this is the transaction nonce, which is 12. This is the amount. The nonce basically is, non stands for number used once, and it's the number of transactions that, not particularly the originating wallet, that's the wallet which originating the transaction, has carried out. So this is the 12th transaction I'm carrying out from that particular wallet, right? And this is the amount I sent, 0.01 Sepolia ETH. Like I said earlier, for simple transactions on Ethereum, you're going to pay 21,000 gas. So this is the normal transaction, and this is the gas price, probably the base gas or the base plus priority fee. And as you can see, this is the total fee I had to pay. So this is total fee plus that's total gas fee plus the amount I had to pay. And this is what it came out. Now this is basically what a transaction is. I don't know if I believe that that illustration should have enabled anybody understand transactions properly. So we're just going to we're going to take a deeper look into transactions, because that's just like a very brief surface explanation. So we just carried out a simple X transfer. So basically, what transactions do is they change the state of the blockchain. So as you can see, before I sent 0.018, right? Before I sent 0.018, Ethereum was at world state T. Now I carried out a transaction and Ethereum changed from world state T, right, to world state T plus one. That was a new transaction that updated the state of Ethereum. Let me see if okay, nobody's joining. That my voice is fading away. Can you guys still hear me? I'm very sorry for how bad the network is today. Can you guys still hear me?
Yeah, it's clear.
All right.
Yes, we can hear you
So
now.
Yes, we can. We
yeah,
can both.
right. So next thing I would want us okay, let's just take a look at some other important aspects. I think we need to check out. We have very little time and we have a lot to do. Okay, so this is also a resource you should definitely check out. Some of these things, please try to read up on them because I promise you, you'll never understand it well, understand it properly from this call. This call is just the idea is just provide you with a base knowledge, but um the blockchain ecosystem is very complicated. It introduces a ton of new concepts you are probably not used to, and you get used to these things by consistent study. So as a blockchain engineer, as a blockchain developer, you need to be keen to study. You need to be ready to read a lot because that's just the only way you'd be able to like scale within this ecosystem. So please just check out most of all this. There's very little we can do because we have limited time. So just check out most of all these resources later and don't procrastinate. Do it tonight because with what we've learned, if you read this thing tonight, you'll tend to understand it better. But if you leave it till like next week, by next week you will have forgotten some of these things I said, except you have the time to go and start watching the 2 hours video, which I'm sure most of us will not do. But if you want to do it, the video will still be available on our YouTube channel. But please try to read up and check up on these materials. So we already explain what a transaction is, right? So a transaction would normally contain some very important properties. So one of them is the from, that's the address, the originating address, the address of the sender, the person transferring money, the person originating a transaction. So if it's a transaction originating from a smart contract, right? The from address is going to be the address of that smart contract. If it's from an externally owned account, the from address is going to be the address of that externally owned account. Now, the recipient is basically the receiving address, right? So if you are sending it, the recipient is basically the address that the transaction is going towards, right? For a smart contract, most times the recipient is going to be an null address, is going to be a zero address, it's going to be an empty field. So, but for transfers, most times the recipient is going to be the person you want to send Ethereum to. Now we have the signature. So the signature composes of three different components, which is beyond the scope of this particular class. So I was thinking we're going to take a look at cryptography, but we're going to leave that for a later class when we've probably gotten a better understanding of blockchains and we'll start building smart contracts. But a signature basically contains three important components. That's the V component, the R component, and the S component. We are going to look at that hopefully during the course of the bootcamp, right? Then we are going. The next thing a transaction contains is a nonce. Like I said, a nonce is a number, stands for number used once, right? And it's used to ensure the nonce helps prevent what we call a replay attack. So replay attack is think of it as an attack in by whereby let's say I sent one Ethereum to Stanley and a scammer want to replay that transaction and somehow make it look like I sent the Ethereum to him instead. So in non-sale prevents that. So you cannot duplicate a transaction because it is impossible to originate another transaction from that wallet address that will have the same nonce as the previous nonce that was used earlier. So Ethereum basically is it carries out transaction in sequential manner. So the nonce increases sequentially. So it indicates, like I said earlier, the transaction number from the account. So we had a nonce of 12, which meant that was the 12th transaction I was carrying out from that account, right? Now we have this value. The value is the amount of ETH that you are trying to transfer from the sender to recipient. So the value can be anything. Then you have the input data, which is optional. You have the gas limit, which is the maximum amount of gas units that can be consumed by that particular transaction. So the gas limit is always specified by the EVM. Then we have the max priority fee gas and the max fee per gas. So we're just going to skip all that. Is there any other thing I want us to see? All right, so there are different type of transactions. So we have three major types of transactions according to the docs, right? So you have regular transactions. So regular transactions are simple earth transfers from one account to another. So if you're going from one externally owned account to another, that's the regular transaction. Then we have contract deployment transactions. So these transactions that are carried out when you want to deploy a smart contract. Now these transactions are unique because the to address is usually missing, right? There's no to address, and data field is usually filled in with the contract code. That's the contract byte code, basically. Then the third type of transaction we have is the execution of a contract. So when you make a call to a public function or an external function that is
You're breaking,
We
Darlington.
can't we can't hear you again, sir. We can't hear you again,
You're
sir.
working, sir.
the contract execution.
Any here, sir?
That's the third type
We are lost. We no longer hear you,
of
sir.
transaction, right?
So
Uh,
we are not hearing you at all. You're not following.
and
Hello, Darlington. We cannot hear you. 1 second. Let me reach out to him. Hold on, guys.
right, can you guys hear me now?
Yes, it's
Yes, we
better.
can.
Oh my God, I really apologize. Honestly, network in Osaka is so messed up today. Like really messed up. Yeah, so I think that will be all. Okay, where did you guys lose me? Let me be sure. Like I got to where I wanted to get. Where did you guys lose me?
So you were
Types of
explaining the
transactions.
regular transaction.
Types of transactions.
Yeah, the regular
Okay, sir.
transaction.
All right, so within the guys can see my screen now, Shay. Is my
Yes, we
screen
can
still
see.
visible?
Yes.
Okay,
Yes,
okay.
sir.
Yeah,
Yes, sir.
so
Yes, sir.
so like I was explaining that there are three types of transactions basically. There are the regular transactions, which is a transaction that is carried out from one externally owned account to another. So I think last time I checked, right, this type of transactions did not exactly update the state of the machine though, because like they they go on from one account to another, so they just update the state of this account, but something I'll probably confirm later. So, but this basically there are transactions that are carried out from one externally owned account to another externally owned account. Then we have a contract deployment transaction. So these transactions are unique because they do not have like a to address. Their recipient address is missing, and the data field is usually filled in with like the contract byte code. Then we have lastly the execution of a contract. So when you make a call to like a public function, an external function, or a view function, basically a public function, external function, view function do not mutate the state of the contracts. Sorry, of this the state of the VM. So we're going to be looking at public and external functions when we start looking at Solidity smart contracts. So but basically when you make a call to or you try to interact with a deployed smart contract, um, this is basically like a contract execution. So it's a third type of transaction. And I said that the rest of this can be read upon, right? Because we are out of time. We have 5 minutes to go. So the rest of the type of transactions can be read upon. So the next thing I want us to look at is blockchain wallets. We're going to be looking at blockchain wallets next. But before then, does anybody have any questions as pertaining to transactions? Any questions as pertaining to transactions? Okay, yeah, something to just unmute your mic and ask.
Yeah, please repeat what you said about execution of a contract. Yes, thank you.
Okay, execution of smart contracts. So I said that's the third type of transaction, and that's usually That usually created that transaction is usually created or initiated when you like try to interact with a deployed smart contract. So you try to interact with the public function or the external function in a deployed smart contracts. You are basically initiating a smart contract execution. So that's the third type of transaction. Then I said you guys can check off the rest of the docs, right, and probably try to. Yeah, Wisdom, you have a question.
All these things now, I was like thinking that maybe you should show us using all the remix to show us all these transactions, like all these
Yeah, don't worry. We're going to try to
we
do
are
that
still going to do
during the
it.
call. Yeah, we're still going to
Okay, no
try to do that
problem.
during the call. We're going to deploy a smart contract. So when we get to the smart contract part, we're going to deploy a smart contract, try to interact with it.
Now we are slowly losing you. We are slowly losing you.
Darlington, I think you're breaking.
So even if we don't do that, so next week we're going to be that remix ID. We're going to start creating or write smart.
Uh, we are slowly losing you.
Yes, it's
We can
clear
hear you
now.
now.
Yeah,
Okay,
yeah.
now.
All right. So because of time, let's just take a quick through wallets. I think wallets is like something a lot of us already have familiarity with. We talked about it also during the blockchain Union conference, right? So blockchain wallet basically is a simple cryptocurrency wallet that allows users to store and manage different kinds of cryptocurrencies. For example, Bitcoin or Ethereum or Solana and so on and so forth. So a blockchain wallet basically helps you exchange funds easily. Now, a blockchain wallet most times is usually an externally owned account. So, but there are also contract accounts like the agent wallet, like the safe wallet. But most blockchain wallets usually find example categories. So we have hot wallets and daily applications. So most times you always interact with like a hot wallet using like your phone or your laptop and so on and so forth. But a hardware wallet or a cold wallet is what you can see by the side that looks like a USB or a flash drive, right? So that's known as a cold wallet. So there is that's a ledger wallet, right? So these are wallets that you can hold physically. They are not on the internet and they are considered safer because it is the chances of having a hacker hack into the software, right, and steal your seed phrase and probably steal your coins and so on is very less. So they are usually considered safer, but they are very much more expensive to get, right? But a hot wallet, you can just simply head to Play Store and download Trust Wallet or MetaMask to start using them. So blockchain wallets are basically what you can use to store transactions, store cryptocurrencies. But then our focus is not going to be on storing cryptocurrencies since we are not traders, right? Well, blockchain wallets are also gateways from which you can interact with smart contracts. So you cannot interact with a decentralized application or an application built on
We can't hear you clearly, sir.
the blockchain.
I've lost you again. No, you can't hear, sir.
If you don't have a wallet, so because wallets are, like I said earlier, externally owned accounts, you can use them to sign messages, you can use them very. Look, can you guys hear me now?
Yes, we can hear you now.
I really apologize. I don't know how many times I would really apologize. I was the network situation really very bad. I'm just trying to change positions, but wait complete so I can proceed.
It's better now. Yeah, can hear you now.
All right. Okay, so I was talking about blockchain wallets, right? And I said I think I already talked about the fact that you can store cryptocurrencies in blockchain using wallets, and not only beyond cryptocurrencies, right? You can use blockchain wallets to like interact with smart contracts. So like that gateway with which you would interact with a smart contract. For example, when we start deploying smart contracts, right, and deploying smart contracts, you know that you begin to realize that you need a wallet to like interact with most of these transactions, as you need to sign a message using like a private key, using your private and public keys, right? So you need to sign messages, and that's one of the reasons why you need wallets to carry out transactions. And I've already established that blockchain wallets are divided into two categories. We have hot wallets, which are examples are popular Trust Wallet, MetaMask, and so on and so forth. Then we also have cold wallets, which you can, and examples are Trezor and Ledger. So they are the two of them are in the picture. The soft wallet is the phone you can see, right? But the hard wallet is like the flash drive kind of thing you can see. So, but the last thing we're going to look at for today is smart contracts. Now we've talked about smart contracts time and time and time and time again. So I kind of believe that it's something that we already have like a basic understanding of, right? So the term smart contract was basically coined by Zabo in 1994, and it's basically like an agreement between two people in the form of computer code. So you know how you can run custom logics on, let's say, on computers using programming languages like JavaScript and so on. Smart contracts are just similar, right? So you have an agreement, you can put them on the blockchain basically as codes, and but the primary advantage smart contracts basically have over let's say softwares that we build using centralized systems or program high level program languages like JavaScript and the rest, is the fact that the smart contract runs on the blockchain, and as such a smart contract is immutable. So once a smart contract is put on the blockchain, we are sure that the smart contract cannot be mutated. Although at the point towards the ending of this course, we're going to look at upgradable smart contracts. But at this point in time, I want us to like understand that smart contracts are supposed to not be mutated, right? So they are basically immutable codes you put on the blockchain to run. All right, so let me just check that. I'm not lost. Okay, so yeah, so basically blockchain technology gives us the ability to decentralize smart contracts so that they are fair and trustless. And I say we're going to do like a simple example using it Remix ID, right? And I'm just going to run through that. A lot of us are not going to understand it, but like I said, not worry at all, because from next week we're going to be looking into the Remix ID. We're going to be studying Solidity. We're going to start looking at different Solidity fundamentals, writing and deploying your smart contracts on like the Ethereum blockchain. So I'm just going to open Remix here. Hopefully it doesn't take the whole time in the world to open, because my network is not the best currently. So Remix basically is an integrated development environment that runs on the browser. So think of it as VS Code that runs on the browser, but for smart contract development and deployment. So with Remix, you can quickly write smart contracts, deploy them, and interact with them. But while Remix has its advantages, right, we would also look at custom local development tools like Hadat, because these tools are usually more broader, and they are usually better for building large scale applications, as you'll be able to run tests, you'll be able to write scripts and a whole lot of other things. So, but for today, for this simple example, right, we're just going to simply use Remix to try to like write and deploy this smart contract. But like I predicted, this is taking the whole world to open. My network is not the best currently. All right, so this finally opened. So I think I have some simple smart contracts in here. So we're just going to deploy one of them. And you load up. Unfortunately, there's no smart contract here. Okay, so let's just create a simple one. Basically, we call this ENS.so. Now, on blockchain UNN's GitHub channel, GitHub repo, right? There's this repository I'm trying to compile, which will just contain basic minimal implementations of different standard and concepts in Solidity, right? And I'm just going to copy the ENS example from that repo, and I'm going to paste that here. Okay, all right. So I'm just going to paste that here, and I'm going to try to compile and deploy it. I hope we are following. Hope you guys can still hear me clearly, right? I'm not
Yes, sir, we are
speaking to
with you. We are
myself.
with
Yeah.
you, sir.
Yes, we can hear you
All right.
clearly, sir.
Yeah. So I just copied and pasted this smart contracts, right? So the simple smart contracts basically that think of it as an Ethereum name service. So we have this thing in Ethereum called ENS, right? That helps you map an address to a name. So using that, for example, I have mine, which is 0x So if someone wants to send me money, right? Ethereum addresses are very long and very complicated. You don't want to cram that. Let's say you don't have access to your wallet, for example, but you want to receive money. Just like your basically you could just give the person your ENS instead. So I could just tell you, okay, send the money you want to send to 0x So if you input that in a wallet, right, you should see my name or my name pop out, right? That's if, for example, let me see if that will work through. Do we have that much time? But just to show you what I'm talking about, right? Let's say we come here and open this, and I'm going to just switch to minutes because it's on Ethereum minute. My end is on Ethereum minute. So let's say I want to send Ethereum to myself, right? And I don't know my address honestly, but I can just simply come here and type 0x. I don't think MetaMask has support for it, but it is actually supported on my Trust wallet. Okay, enter public address 0x. Yeah, it's actually supposed to have support for it. Let me try it. 0x Darlington.net. No address. Oh, zero, not oh, 0x Darlington. Yeah. So as you can see here, typing 0x Darlington.h, you can see my wallet address just pop up. And you can just simply send Ethereum to this particular address using just my name. All right. So that's what we are. We're just trying to build we're just trying to build a simplified version here using this. So that's what the smart contract does. So basically we just associate or store the name in a mapping of address to name, and we have a function to get the name. So we're going to try to deploy our smart contract. So now we're going to just simply come here, and we're going to compile this first of all. So after compiling our smart contracts, now the process of compiling your Solidity smart contracts, you are basically just generating or stepping down the high level language to bytecode instructions, or a bytecode instruction set, which is like what the EVM understands, right? So I'm just going to come here, and we can deploy to a local environment such as the Remix virtual machine, or we can decide to do that using a wallet. But we can't do it with a wallet, as I don't have MetaMask installed on this particular profile. So we're just going to deploy it to the local virtual machine directly.
We can't hear you. We can't hear anything.
Is it only me?
So we can't hear you.
We can't hear
Darlington, I think
you.
you're muted.
Sorry, my mic was muted. I don't know how that happened. Oh my god. Can you guys hear me now?
Yes, we
Yeah.
can hear you now.
Apologies. All right, so I think he gets muted. I don't know if it stops. Okay. Yeah. So I what I did basically was I just deployed the smart contracts, right? As you can see here, this is like the logs for the deployed smart contracts. So this was the transaction hash that was generated. This was the block hash, the block number, and so on and so forth. The contract address. The contract address is the address of the contract that was deployed, right? The from address, that's the address which this contract was deployed from, and then the to and so on. You can see the gas and every other thing here. So to get the, let's see now. So if I paste in that address here and I click on get name, right, you can see that I get back Darlington. Now there are two things here, right? We have the external or the public functions, and we have the view functions. So the external or public functions are the contract execution I talked about in here. So in here I talked about when we were talking about types of transactions, right? I talked about execution of a contract. So let's say when I try to store a new name, when I try to store a new name in this remix contract, so let's say I click on store name and then I want to store a new name for that particular, sorry, um, I don't have a wallet. Okay, yeah, let's say I want to store a new name, right, for this particular address. So let's just say Chisholm, right? And I just simply click on transact. Now this is a public transaction, and it mutates the state of the blockchain. So it will change the state of the Ethereum world machine, right? And as you can see here, for this particular account now that I used to deploy this transaction, you can see that fees were was subtracted, right? So before it was 100 ether, but now we have just 99 ether. All right. So now if I come here and I try to get the name for this address, you can see that I get back Chisom because Chisom was stored on the Ethereum virtual machine on the Ethereum blockchain. So that's just basically about it with smart contracts, transactions, and so on and so forth. So if you don't have a clear understanding of this, don't worry, you're not too bothered about. The idea of this class is right was to give you foundational knowledge for you to build upon. So with the next classes, things will become easier. When you begin to practicalize these things, you begin to write your own smart contracts, deploy them, interact and play with them. You begin to and you keep reading up on materials. You begin to come to better understanding of how these systems work. All right. So I don't know if you have any questions before we go to the last parts. Any questions before we go to the last part of today's session?
Okay, so you said the next class will start coding. So I'm like, what do we need to install?
Okay, then since you need to install for the next class, basically you're not going to need to install anything. Just ensure you have Chrome because you're going to be working with Chrome. So for the next class, just ensure you have Chrome or Brave browser. You have a browser installed, a stable network internet connection. Just come to the class and pay attention. But that's for the next two classes, right? Where we're going to mostly be doing things remix. So, but from the third class, we're going to start working with we're going to start working with hard hats. That's when we're going to need to start installing stuff. And the instructors will communicate with you on the things you need to install. Chukwemeka, please can you mute your mic? All right. Chidwin, you have a question?
I've muted it. It's network. It's network that's causing
Okay.
it.
Okay. My question is, I want to know when the assignment is. Do you have assignment for this particular class?
Chidwin, you have a question?
Yes, I want to know when.
Chidwin, if you have a question, can you mute your mic? I can't hear you.
Okay, can you hear me now? Hello. Can you hear me?
Yes, we can hear you.
Okay, I want to know whether we are going to have an
Yeah, we have a
assignment for this
class work
particular
now, which
class.
is going to just happen right now. And
Sorry, I know you are breaking,
we
sir.
already have a lot of persons. I don't know if we have everybody
Darlington, I think you're breaking. You're breaking.
So I think
for
you're broken. We can't hear you clearly.
it's not an assignment, it's a classwork. You're going to do it now and submit it before we leave the you're going to do it and submit it before you leave the class right now. Yeah, I can hear you. Yeah, I can hear you. I can hear you. I can hear you.
Yeah, you were breaking.
Sorry, sir. Are you with us?
1 second, I think his network is bad.
All right. Can you guys hear me now?
Yes, we can hear you. We lost you
Yes, we
for
can hear you now.
the
All
last
right.
10 minutes. We're not hearing what you were saying.
Yeah, apologies. I think we already done with class, right? I was just about to give us the classwork. So basically how the classwork works is it's a Google form and everything has already been everything yeah, the questions have already been imputed. So what I'm going to do now is I'm going to drop the Google form in the chat and we have just 15 minutes. So we're going to be leaving the call. This is nine, let's say this is 9:20, right? So once I drop the link on the chat, right, by 9:35, I'll be closing the form and we'll be ending the class for today. So please and please and please, once you see the classwork, that's the Google form link, just start attempting the questions, try to answer them to the best of your knowledge. I would advise, I know you have access to the internet, but I would advise don't use the internet to answer them. But just try to answer them. And these assignments, these classworks are very important. So please try to do your best. All right. So let's see if I can network even allow me get the link. Yep, so I'm just shorting the URL to copy it. All right, so I'm going to paste this in the chat now. Like I said, you have just 15 minutes. By exactly 9:35, I'll be locking the form and we'll be calling it a day. So you guys can see the classwork, right? So you can see the classwork. Is there anything you don't understand you want to ask? Any
We need
questions?
permission for it, sir.
Permissions.
Permission, boss, permission.
Oh, sorry about that. Mm, oh, down to. Let me just stop sharing this. Let me know when my program is. Right, can you guys try accessing it again? Can you guys try accessing it again and please confirm if you have access to it?
I don't still have access to it.
Is that same for everyone?
Yes.
Please, yes, I can see it.
Okay, a minute. Yeah, sorry about that. A minute, please. All right, you know what? Okay. Sorry about that, but we are actually out of time. So what I'm going to do instead is I'm going to send this to the group chat instead. I'm going to give all of us the right permission. I don't know if we need our emails to do this. I can't exactly remember, but I don't think I'm supposed to get emails to do this. I will just check out, pair out with the permission thing, and I'm going to okay. I'm actually in the right tab. Yeah, I'm going to send the link to the quiz later on the group chat. So please just attempt it. There's going to be a time when it closes, which is going to it's not going to be a very long time. So please just watch out on the group chat. I'm going to be sending it in the next 10 to 15 minutes just after we are done with the call. All right. So yeah, it's supposed to be a settings thing, but it's been a long while since I played with the form. So it's Google form. So I'm just going to try to fix that later. But just not to waste our time. I think today this would end the class or the introduction section. So any more questions? We can take two more questions. We still have 7 minutes before we go. If you have any questions, probably just raise your hand and let's try to take that before we go. All right, I can see Chukwemeka and Chidibim's hand. Chukwemeka, let's start with you.
Okay. Okay. Thank you very much, sir, for the opportunity. Well, is there was regarding the when you are talking about the remix?
Okay.
Is there any point can you hear me, sir?
Yeah, I can hear you.
Okay. I'm talking about when you are saying something about the remix, how to deploy and contract. I didn't get a hang of it. I don't know whether there's any material I can read up to get a hang of it, or maybe follow up probably for the next class so I can be able to be.
Yeah, sure. We're going to be looking at it in the next class, but if you want to resource beforehand, I think Chidera can drop something on the group chat. Chidera, maybe do you have any resource you could probably drop on Remix that could probably show them their way around?
Yeah, sure.
Thank you very much, sir. Thank you very much. I appreciate it.
All right, you're welcome. Okay, then let's go with Chidibim before we go. Chidibim, do you have a question?
Okay. My question is it possible for us to have anything like group project in this boot camp, like a project that we do collectively in a group?
For now we can't see, but we're going to put that into consideration as the boot camp goes on. But for now, the expected the way the boot camp was programmed, right? So most likely do things individually. But if there's any need for a group project, we would communicate that with you guys.
Okay, thank you.
Yeah, you're welcome. Okay, I think that would be it for tonight. So please just watch out for the link on the group chat, because once the form is locked, the form will be open for, instead of 15 minutes, right? The form will be open for 30 minutes after I drop on the group chat, so everybody can get access to it. I'm going to try to tag everybody. So please try to just try to answer the questions and submit before the form is locked. I can still see two hands up. Build that.
Yeah, basically, I have not a question. I don't have access to the group. Like, I'm not on the group.
All right. Just send me a message. I'll add you to the group chat.
Okay.
Some Tochukwu.
Yeah, please try to mention everyone when you post the link to the Google documents, please.
Yeah, sure. I'll do that. I'll do that.
Daniel,
All right, Daniel. Yeah, Daniel.
Okay, okay, hi, good evening. I wanted to ask, are we going to be using JavaScript for this?
When we get into the harder section, right? So we're going to using JavaScript to write deploy scripts and do a whole lot of interesting things. If you notice, that was one of the reasons why the requirements for joining the bootcamp was that you are proficient with JavaScript. So
Yeah.
JavaScript is definitely going to be extensively used.
Okay, okay. Okay, thanks.
Yeah, I think that will be about it for tonight. If you have any more questions, just drop it in the group chat. Let me go work on the form now and it will be available soon. Victor, okay, let's just take Victor one last question. Victor, what do you want to ask?
Okay. So when you say JavaScript, do you mean Node.js for backend?
Just plain JavaScript, no Node.js, no. You're going to need the understanding of React, but you're most likely not going to use Node.js to do anything, but plain JavaScript for writing scripts, and we are probably going to need React for building front-end interfaces. Those are the two major things you probably just need.
Okay. Thank you.
Yeah, all right. I think that will be about it for tonight. Thank you everyone for coming around. I greatly apologize for the network issues, but to be really honest, I wish I could do something about it, but there was very little I could do. I just really hope that network will be very much better by the next class. And I think that will be about it for tonight. Thank you so much for coming around. Thank you so much for sticking around. And I'm sure before we done with this bootcamp, we of course will be leading with very proficient knowledge in blockchain development. Yeah, good night, everyone.
Good night, sir.